All right, well, hi, welcome everybody. Glad that you could all make it. I see a few familiar faces out there. Thank you, Azuma-san, for coming. So today, yeah, I'm sure you've seen the safe harbor statement a whole bunch of times, but I kind of just want to reemphasize it for this talk because everything I'm talking about in today's session is experimental as of JDK 9 and not officially supported in any way. So usually we just kind of pass right through these things, but in this case it actually is kind of important. So please don't build your entire production system based off of the AOT technology we're going to talk about today. So a few people in the audience I think know me, but just for those of you who don't, I'm a JVM sustaining engineer, which means I fix post-release HotSpot bugs. That's my day job. I'm also the JDK updates project maintainer, or one of them. So you can find me sometimes arguing with people online about what kind of changes should and shouldn't make it into update releases. I've done Java 1 before. I'm co-author of Japan's best-selling WebLogic book, and I do Twitter and have a blog. So we don't have a whole lot of time to talk today, so we're going to kind of try and keep things fairly simple. Now, this is one of 3 different AOT talks that I'm aware of at Java 1 this week, and fortunately the other 2 talks are all tomorrow. So if you weren't planning on necessarily attending them tomorrow, maybe you can fit that into your schedule, because some of the upcoming talks look pretty interesting and good too, and I have some pointers to them at the end of the slide deck. But for today, this is kind of an introduction to the feature itself. We're going to start off at the very beginning and kind of introduce what AOT is and what the goals are, the design goals for this new feature and what you might hope to get out of it. So we're going to start off with some kind of boring warnings just to make sure that there's no misunderstanding and that everyone takes everything I say with a little bit of grain of salt. So the first thing is that, like I said before, it's not yet officially supported. Sun and then later Oracle kind of has a long history of introducing new features this way. Other examples might be tiered compilation, the G1 compiler, the G1 garbage collector, garbage first. These are all features that originally entered the product as an experimental feature that was not officially supported, and then they became supported, and then later they became the default. Enabled right out of the box. And so while we don't know for sure whether AOT will take a similar path, there is kind of room for optimism. But as of now, it's not something that you can really expect official support from Oracle from. That said, if you do find a bug, please file a bug report. We want to know about them. We want to fix it. We want to make this as high a quality as possible. As of today, it's only supported on Intel 64-bit for Linux. And also, just as another requirement, you have to have libelf installed. That's no biggie, you just apt-get it before you build or whatever, but it has to be there. And so hopefully we're planning on adding other platforms as well in the future, but for today, this is the only one that you can use this on. There's also no official documentation, which hopefully I'll kind of fill the gap a little bit with today's session. The only official thing out there really is the JEP document. And again, right now we don't know when or even if official support will follow or in what time frame certain platforms may or may not be entered. So that's all the boring boilerplate I had to get out of the way. Let's actually jump into AOT and what it's all about. So given all the things I just said, why would you bother learning about it if you can't, really use it in production yet? Well, for one thing, it's pretty darn likely that this may be supported in the future. And so just in the same sense that you want to get a hold of EA builds, early access builds, and play with them to learn about the direction the platform may go in, this is your opportunity to get a jump start on what may be a very important and exciting technology being introduced to the platform. The other thing is that, like most of my talks, we're going to jump off on a few random tangents that brush up against other features of the HotSpot JVM. And so it's kind of a good excuse to just kind of cover some interesting material. And also, if you're anything like me, you just think this stuff is really cool and a whole lot of fun. So it's always good to kind of explore and get a peek under the hood. So everyone's really interested in this because this is a fundamental change or addition to Java's execution model, that's been kind of in place since the beginning of time immortal. So originally we had, you had your Java source code, you compiled it with Java C, you get a class file, and then you run that on the runtime. This should not be surprising to anyone. And then, of course, in the Java 1.2 timeframe, we started adding JIT compilation into the mix. And so while you were running your application on your runtime, the JIT compiler would emit actual machine code that would be stored and run from memory. And JIT compilation has many advantages. The idea here is that methods do get compiled, but compilation is expensive. Compilation is always a very resource-intensive exercise. And so both CPU cycles and memory are being consumed, and your application's execution threads are basically competing with the C1 and C2 compilation threads for limited resources or finite resources in your application. But once we do get over that hump and we get the method compiled, the machine language versions that we emit run very, very fast, and this gives us the peak performance that we expect from Java today. But one reasonable question is JIT compilation really always superior or better than just a pure interpreter implementation? And we kind of have as a possible case study of that, JRocket. So I didn't mention in my self-introduction, but I actually come from the JRocket side of things originally. And we had a pure JIT, kind of like a classic JIT implementation where we didn't have an interpreter like HotSpot does to fall back on. So everything just got JIT compiled by default. And so does this really give you better performance, this kind of militantly trying to compile everything to machine code? And the answer is, well, what's your definition of performance? So kind of an extreme example, and I know this is profoundly unfair to Java, but on the left here, I'm running just a native hello world, that was written in C. This comparison means nothing because obviously something written like that versus a full runtime with garbage collection and everything else Java brings to the table, you're not going to compete. But the idea here is that people really do look at these types of use cases and are asking themselves, why does Java take so long? So there's always been this pressure to try and make Java start up and run as fast as possible. And so the point of using Hello World here is that just out of the box, even executing anything, the JVM is kind of behind the native world in terms of startup time, and people notice that. And so whether the comparison's fair or not, people make that comparison, and it's something that we have to be aware of, and that kind of motivates us to try and improve on these times as much as humanly possible. So JIT compilation isn't always fastest, and that's why we have the HotSpot way of thinking or philosophy where we don't JIT compile everything like JRocket did. So like I said, the overhead for compilation is extremely high, and so we're consuming resources like memory and CPU time, but also another issue that people are not necessarily always aware of is that there's also a latency involved with JIT compilation. And what I mean by that is that even though we have the interpreter that can start running the code immediately, and we can asynchronously do the compilation in a separate compilation thread, there's a delay before we get that compiled version. So there's a delay before we hit the peak performance for that particular method. And so in the sense, we get to run it immediately, but we're running it slow. We're running it in the interpreter. And what we want to be doing is we want to be running it, the fastest version of that method, the compiled version of that method, as fast as humanly possible. So in HotSpot, what we do is we start off, every method begins with being interpreted. That's the default behavior that everything gets. And then we're constantly doing what we call HotSpot profiling, which is basically just collecting, doing a stop the world and seeing what all the threads are running and keeping track of all that. And then we have statistics for invocation counts and things like that. The interpreter actually gives us most of that information for free. But anyway, so we have all this information, and then we identify which methods are hot, and we only JIT compile those, and then the interpreted ones just remain interpreted. So things like static initializers and other stuff that just there's no value in paying the overhead cost of compiling. We just avoid by compiling, or by not compiling at all. Okay. But even with HotSpot's JIT, there's still some very bad kind of weak points that we have to deal with. Application startup time is still an issue. It takes longer. We have a warm-up period. So even after your application starts responding to incoming requests, it still may take a while before enough of the hot methods get JIT compiled to machine code and we start seeing peak performance. So startup time is one measure, and then time to peak performance is another measure. And they're both things where there's possible room for improvement in the current compilation model. And again, we're consuming a lot of resources, most notably memory. And as kind of a side thing, not so much of an issue with Oracle's product offerings, but there are some platforms out there that, for whatever reason, disallow the dynamic generation of machine code at runtime. And so if you wanted to run the JVM on them, you're kind of stuck with an interpreter unless you can find some way around that. So this is something I talked about in my session yesterday, and I think most people are familiar with this, but there's two separate compilers that are built into the HotSpot JVM. C1, which is for client use, which kind of just does a quick and dirty compilation. The idea is to kind of finish the act of compiling and get that quicker machine language version of the method available for execution as fast as possible. Then there's C2, which is the server compiler, and that one spends a lot more time, i.e. resources, on doing very heavy optimization to give you the most performant code as possible. And one of the key differences here is that C2 can't just run out of the blue. C2 depends on having a whole bunch of profiling data that was collected by the runtime before it compiles a method. And so without that data, we can't really C2 compile methods. And that'll come into play later in a few more slides. So that's the current situation as it exists kind of today or before JDK 9. So what does AOT bring to the table here? Well, the idea is, of course, because it's ahead of time, is to generate machine code before the runtime, before we actually run the application. So this is kind of just like traditional static compilation. And so the JVM hopefully can find and load that code during runtime, and then we bypass the latency and the overhead of compilation work while we're running. So this is the kind of standard model that we have today. Again, we just saw this in a few slides ago. And the addition here is that now we have this new tool, this JAOTC, Java Ahead of Time Compiler, and it's going to give you an ELF shared object or shared library that you can load into the runtime, and it use that pre-existing machine code to start up as fast as possible. But there's some other benefits here. And so in a traditional model where you have multiple JVMs running and they're all running the same code, like say some sort of redundancy or clustering within the same OS VM, each JVM kind of gets its own copy of it. So not only you're paying the performance cost of compiling it all those times, but then once you have the output of that act of compilation, once you have the actual machine code, that has to be kept in the code cache. And the code cache takes up a lot of space. Especially with the introduction of tiered compilation, our code cache size expanded by about 5 times. And so if you run a lot of JVMs on the same OS instance, that can actually be a lot of unnecessary redundant overhead. So AOT allows us to create these read-only segments in memory that have the machine code in them, and that can be shared across multiple JVM instances. And so we have a density improvement where if you're deploying all these different JVMs to the cloud, the total consumed memory is going to be less. So there's a lot of advantages here. It's going to give you faster startup times. This is just, as soon as your application is ready to start actually taking and processing requests, that's going to improve. Then we have, beyond that, faster warm-up times or less warm-up time. And so even though it's taking requests, like I said a few slides earlier, it takes a little while before you reach peak performance. But with AOT, because a lot of those hot methods are already going to be available, we can reach peak performance much faster. And of course, because we're not doing that compilation at runtime, we also have less memory footprint. We have less overhead for compilation to compete with your execution threads for your application that are doing real work for you. And of course, we're getting the space savings, the density improvements if you're running multiple JVMs that are running the same code. And now we can run on platforms that, for whatever reason, might disallow runtime generation of machine code. So I have little stars next to all this, and what I'm saying is your mileage may vary. And so what I mean by that is like a lot of options like tiered compilation or different GCs, garbage collectors, you will find that some applications benefit from these changes and improvements, and other ones might even have performance regressions from it. It's very hard to say. There's no silver bullet that kind of improves all cases, and that's one of the reasons why this technology is not really officially supported yet, and it might be even longer before it would be on by default, and that's because really there's cases where this actually doesn't help. But for many applications, we've seen improvements in that. So I'm sure there's a few people in the audience that are going, quicker warm-up times, quicker startup times, sharing data among different JVMs. All this sounds pretty darn familiar. Like, why do I think I've heard all this before? And the reality is there's actually a number of other pieces of functionality that have been added to the platform in the recent years that kind of have very similar design goals to what we were trying to do with AOT. And so I just want to cover those really quickly to kind of put everything in perspective and see how AOT kind of fits into the larger picture of startup time performance improvements that we're trying to do. So the two big ones are tiered compilation and class data sharing, and also app class data sharing. And of course, with the announcement that we're basically taking all of what are currently the commercial features of the JVM and making them open source, for the first time, OpenJDK users will also be able to take advantage of app class data sharing in the very near future. So tiered compilation, it's a pretty complicated topic of its own, so I don't want to dive into too much detail here, but basically the idea is that we no longer have to make the choice between using the C1 compiler or the C2 compiler. We actually use both. And so traditionally the server JVM would just have the interpreter, which would run for, say, 15,000 executions of a particular method, and then it would compile it using all the profiling data. And with tiered compilation enabled, we now have a midway point where we use the C1 compiler to generate instrumented code that collects the profiling data needed by C2, but also is much quicker and easier than a full C2 compilation. So we kind of get the best of both worlds. We get a really quick compilation that happens very early on in the life cycle of the process, but it's fast enough that it's dramatically quicker than interpreting the Java bytecode directly. And that kind of makes things faster until later C2 can come in and then give you the real peak performance. It's a nice, happy middle ground. We also have a class data sharing. So in a traditional situation, and this should look very familiar to a few slides ago, we have the same class is being loaded by multiple JVMs on the same OS instance. Each JVM is going to go through all the effort of parsing the Java bytecode and turning that into the internal data structures that are used by the HotSpot JVM. Traditionally, those were stored in the permanent generation. Now that information's been moved over to what we call the metaspace in JDK 8. But the point is that it's consuming genuine memory. So with class data sharing, the idea is that you would create an archive that would sit on your file system, and that would actually have kind of pre-parsed or pre-digested versions of the class data. And so the JVMs could share that, and that would give you a faster startup time because you're not actually parsing the Java bytecode. And it would also give you some density improvements because you're sharing that across multiple address spaces. So there's actually two different forms of class data sharing. There's the standard class data sharing that's been around for quite a while. I actually don't remember when they added that, somewhere around the 5 or 6 era, and that's kind of free to everybody to use. It's never been a commercial feature, but it only works with the JDK classes themselves, i.e. what used to be part of rt.jar. So the Java SE class library was really the only classes that were compatible or that worked with the traditional class data sharing. Then there's app class data sharing, which, as you can probably assume from the name, means that it's the same class data sharing technology, but applied to your own classes within your application. And so with app class data sharing, you can actually do the same thing with your classes and share them across kind of pre-parsed versions of them across multiple JVM instances. And today this is a commercial feature that's not part of OpenJDK, and you don't get to use this without paying Oracle money. But in the future, in the very near future, just with Java Flight Recorder and all the other great stuff, we're actually bringing this into the open source. And so this will be part of OpenJDK in the very near future. So just to make clear what the differences here are, so the reason this all sounds probably really familiar for you is because a lot of these design goals are the same. Tiered compilation, the killer app, so to speak, for that, faster startup time and faster, or at least a less noticeable warm-up gap. And then class data sharing, app class data sharing is also giving you quicker warm-up time and some better memory efficiency by removing the redundancy that would otherwise be there for having multiple JVMs load the same classes. But what's different from all these, what makes AOT unique, is that none of these involve the output of the JIT compilation process. So AOT is all about what would be within the JVM's code cache. This is actually the machine code that's generated. All of the class data sharing and app class data sharing saved the metadata about the classes, but it didn't actually do anything with generated code. So AOT is really a first for the platform. And all of these technologies work together. It's not a mutually exclusive situation where you have to choose one over the other. And we found in our performance testing that they actually really work best if you use all of them at the same time. So AOT represents another incremental improvement in our goals of faster startup time and better memory usage. So it was suggested before I did this particular talk for Java Day Tokyo that I could better humanize my presentations by having more pictures of people. And I was given this slide. So this brings the total of pictures of people to 10. This entire presentation, which is a pretty good average. I think most of my coworkers have only 5 or 6 pictures of people. So I don't think anyone's going to complain anymore. Usage. So this is where we get into the meat of the thing. So as I already mentioned, we have this new tool, JAOTC, and it's sitting there just right next to Java C and everything else in your bin directory. And using it is pretty darn simple because you have to actually explicitly label the output. Otherwise, you get a really horrendous default name. I think it's output.so or something. It kind of reminds me of GCC, but anyway, you just tell it what the name of the library that you want to generate, and you feed it your class, and it will give you that shared object file. And of course, there's rather extensive online help that will be useful, especially if it's a new tool. And you'll notice if the default invocation kind of follows the Unix philosophy of don't say anything unless stuff goes wrong. And that's to be compatible with all your standard tools that assume that any extraneous output represents some sort of error. But you can change that with the info flag, and that kind of it's like a verbose setting, and that will actually tell you what it found in the class file and what it decided to try and compile. So you can kind of prove to yourself that it's working as you expect it to do, which is kind of important to do the sanity checks when you're using a new tool. So there's a few gotchas that are kind of interesting. One is that by assertions, which most people never bother to enable, actually has to be known at compile time. And normally with JIT compilation, this isn't an issue because the JVM knows if you have assertions enabled or not. But one thing that can happen is if you compile without assertions enabled ahead of time, and then you run it in your JVM, you think during the runtime that just by enabling assertions there that you're getting all of your assertions turned on, when in reality, anything that you compile ahead of time with this tool will not have the assertions enabled. So if you want to have those assertions on, you have to make that decision when you do the AOT compilation. And this flag, this compile with assertions, lets you do that. I think we have the compile commands flag, And this is simply just a way to kind of bail out of compiling specific methods. In the future, we might expand this. We might add other options or settings or whatnot. But as of today, the only thing we support is excluding individual methods, or you can use wildcards to say exclude an entire package. And so because this technology is new and we haven't exactly worked out all the kinks, there are cases where you'll have problems where a particular method might cause the AOT compilation itself to fail, or perhaps even worse, the method might be compiled, but it might be compiled incorrectly, and so the generated machine code might have some sort of problem in it, and so at runtime, that problem manifests in some sort of scary way. And so what you can do is, if you find that there's a particular method that's causing a problem, well, first thing is I'm hoping that you'll send us a bug report if we don't know about it already, but the second thing is that you can use an exclude line in a compile commands file, so you can just tell AOT to compile everything but that method, and then continue using it. So it's not just classes. The kind of hello world example is just doing a class, but in practice, what we usually want to work with is either an entire module at a time or an entire jar file at a time. And AOT has no problem doing that. It'll just suck the entire thing up. One thing I want to point out is that compilation, as I've said several times already, is extremely resource intensive. And Graal, which is the compiler that we use for AOT compilation, definitely uses a lot of memory and a lot of resources. And because this actually happens in Java, this is all Java software that does the compilation for us. This isn't native code. We actually have a heap that you can run out of. And so, for example, if you're compiling the entire Java base module, I found recent builds that I need about somewhere between a 5 and a 6 gigabyte heap just to compile Java base. So if you pass this command line today to the AOT compiler, it'll actually throw an out of memory error on most systems, because most systems you're not going to have a default maximum heap size big enough to handle all this. So if you're going to compile something big, just be prepared. And this is like a huge chunk of the JDK, so it's not that surprising. But be prepared to give it lots of memory and a lot of time. I think this usually takes about somewhere between 20 and 30 minutes, depending on how fast your machine is. It's pretty intense. So the other thing is that and this syntax is not unique to the AOT compiler, but you should be aware of how to pass options. So of course, like for example, if you want to set a larger maximum heap size, this would be the way that you do it. And this is the standard format that Java C and a whole bunch of other tools use that allow you to pass things to the JVM running whatever it is the tool that you're trying to execute there. But this is actually way more important than you would normally assume, and I'm going to explain why in a few more slides. But just know, so it's the standard -J and then whatever JVM option you want to pass. Hi.
Does it only compile classes which you give it? So when you compile a jar file, does it only compile classes from this jar file, or does it take into account classes from Java base or somewhere else?
No, it's only going to be what you explicitly hand it on the command line. It won't go behind your back and compile anything, for better or for worse. There's another option. This ties into the tiered compilation that I introduced a few slides ago, and there's a compiled for tiered option. So it turns out that internally, the AOT tool does not use the same implementation for compilation that the HotSpot JIT compilers use. Like I said, we had 2 JIT compilers. We have C1 and C2, and a lot of people assume that, well, obviously the AOT tool is going to use that code base or that implementation to compile. But it actually uses Graal, which is part of the Oracle Labs work and study into JVM technology. And Graal produces code that is uniquely different from C1, C2. And performance-wise, it's actually somewhere in between. A lot of testing that we've done shows it to somewhere about maybe 10% slower than C2, which is pretty darn good. But you're not getting the full peak performance that you'd get from a legitimate C2 compile. And probably the missing piece there is the fact that we don't have the runtime profiling information that C2 can take advantage of when it JIT compiles stuff. So the actual ideal situation for peak performance is, as I said earlier, to use AOT as just one component in your strategy for getting the best performance possible. And you do that by saying compile for tiered when you AOT compile. And so what that does is it doesn't generate the default growl code. It tells growl to include the profiling instrumentation that C2 requires for it to compile. So you actually end up with the same kind of scenario that you do with tiered compilation, except the middle step is no longer C1, it's the AOT compiled growl code. And that will be just a precursor to what will hopefully eventually be the C2 compiled code. And so you don't have to, you basically get to have your cake and eat it too here as well. You get the immediate performance advantage right out of the gate of having pre-compiled code there, but then eventually the JVM on its own time can loop around and see to it to give you that extra 10% bump. So what does this actually do when you run it? When I actually first proposed this talk, I was like, well, we're going to do a whole bunch of demos. And it turns out the demos are like not horribly exciting because, well, this is, it works, right? And there's nothing here that would tell you that, you know, the library that you actually created was used. So what can we do if we actually want to verify that that was actually used? Well, there's an option, there's a new option that's been added to the JVM called print AOT, and it's disabled by default, obviously. But if you put that in and you run it, you'll actually get some output that's going to look a little similar to the print compilation output that we're all pretty used to seeing. And this is telling you two important pieces of information here. One, that it was able to find the library and load it. And the other two things is that there were two separate methods that were identified and loaded into or kind of acknowledged as being part of the code cache. And that's the constructor for the class, and then the actual hello world main, which you guys don't need to see the source code for because it's as boring as you're imagining. So let's try the same thing. So let's go, and I'm going to disable compressed oops. So just to get an idea, how many people here are familiar with compressed oops, compressed references? Okay, so about 2/3, so good. I'm going to go into a little bit of detail, time permitting, a bit later in the slide deck about those. But you know, a very common thing is that you might want to disable compressed references or compressed oops for whatever reason. So here we're starting the JVM, and I'm just disabling that, and everything else is just like it was on the command line earlier. And you'll see that I actually get an error. It tells me that, hey, you wanted to load this AOT library, but it's actually was compiled with different settings than what the JVM runtime is set for. Now, notice it does actually run the code. Nothing actually broke. So even when we fail to load the AOT library and use it for whatever reason, your application will still run. You'll just get a little warning if you have the print AOT. If you don't have the print AOT listed, it'll actually silently fail to load the AOT library. Which may or may not be the ideal behavior, but it does kind of follow along the philosophy of not breaking anything that currently works. So the idea here is that you need to match your runtime with the compilation. So the options that you use during compilation have to match the options that you use during the runtime. And here I'm just pointing out that if you took away, I'm reiterating basically, that if you take away the print AOT thing and you run it, this is still failing. This is exactly the same command line that I was just passing, except we don't have the verbose AOT output. And so it's silently failing to load that for you. But we have to match these options. And the current kind of documentation, so to speak, the JEP document, which is the closest thing we have to any kind of official documentation for AOT currently, just simply says that you need to match the options, but it doesn't really say which options you really need to match, although it's implied. And in practice, there's only two things you need to worry about. You need to worry about which garbage collector you're using, and you need to worry about whether compressed oops is enabled or not. And it's kind of interesting to think about why that's the case. But just to to summarize here, so you can think of every single compile, AOT compile, and every single run as falling into one of these 4 quadrants. So each of these can just be thought of as a binary thing, and it's either on or off. And they'll stick you into one of these things. So as long as you match your AOT compile with your runtime settings, then the library should be loaded. And we make sure that it sanity checks it when it loads the library so that you don't ever end up loading something that is incompatible with the runtime. Additionally, we also, of course, check that the class hasn't changed. So there's code in there that basically fingerprints classes. We don't really intend for like malicious users to try and do anything sneaky, so it's not like a cryptographic sound hash or anything like that, but it should be enough to prevent you from accidentally making a change to your class so the bytecode doesn't match the library that was produced from AOT compilation of that same bytecode. So why do we need to synchronize VM options? That seems like a really arbitrary kind of pain in the butt thing, right? Like it's a usability issue. And there certainly is room for improvement here, and that is kind of on the internal roadmap to hopefully make this work a little bit easier or better, or at least be a little more intuitive. But today, you really can't do what we refer to as cross-compilation. And what I mean by cross-compilation is I'm not talking about from one CPU type to another, but even like from with compressed references, using a JVM running the AOT tool that uses compressed references to a runtime that doesn't use compressed references. We don't currently support that. So why don't we support that? Well, if we look at the compressed reference or compressed oops, and oops, by the way, is everyone familiar with the term oops? Or okay, so an oops just means a reference. It's a pointer to an object on the heap. That it stands for ordinary object pointer. And it's kind of a strange name, but it has a lot of historical precedent. So Smalltalk and Self apparently used this term, and that's why we've inherited it. And of course, the HotSpot JVM kind of evolved from a Self runtime. So there's a lot of history there for using that term. But when you hear oops, just think of object reference. It's a pointer into the heap somewhere. So compressed oops is, well, a compressed object pointer of some kind. So what the idea is that originally, when we made the move from 32-bit to 64-bit, there was a performance penalty that you were paying. Even on a platform like Intel, where you were getting all these additional registers and stuff, and so you normally expect kind of a speed up when you go to 64-bit because the register pressure was relieved to a great extent. But the slowdown was a result of the fact that all of a sudden all of our references are 64-bit. And of course, this isn't Java specific. I mean, all software kind of has the same problem when you move from 32-bit to 64-bit, is that all of a sudden you have this bandwidth cost between memory and the CPU because all of the pointers are now twice as big. So for the heap, maybe we could do something to alleviate that overhead and to kind of make that regression just magically go away. And the cool thing is the guys at Sun did find a way to do this. And actually, I think we did this at JRocket first and they copied us, but I'm not entirely sure what the history there is. But anyway, maybe we both came up with the idea at the same time, but the idea is pretty simple. It's what is if the heap is actually smaller than 4 gigabytes, then you don't need a heap address space that's larger than 32 bits. So what you can do is just stick the heap somewhere in your in the process's address space, and then just add the offset of wherever that heap starts to every heap reference. So you basically can address an entire 4 gigabyte of heap without having to store 64 bits of every address. And this has a tremendous impact on the performance, not just of speed, but of size, because all of your objects, any object that has a lot of references in it to other objects, pointers to other objects, becomes significantly smaller. So it can actually make your heap consumption smaller as well. So this is great. But how does this actually get implemented? Well, like I said, there's, we break the 64-bit pointer into kind of two halves. And so there's a 32-bit least significant bits, and then there's 32-bit most significant bits. And the idea is that these are not going to change, right? If you have a heap that's under 4 gigabytes and you align it correctly so it's not sitting on a border between two different, kind of 32-bit address space pages, in a sense, then this will be the same for all of your pointers. And so we can just like throw that away. We don't need to keep that information handy. And so this is what actually gets stored in every field of an object on the heap that's pointing to another object. And that's all fine and dandy, but then how do we actually use that? And so in the code that's generated, when we're actually looking at a reference, because obviously on the 64-bit platform, if we have a pointer that's in a register on the CPU or somewhere in the thread's execution stack, it has to be a real 64-bit pointer, right? So how do we expand it or uncompress it? And basically all we do is just we add the base address of the heap to it. So it's very simple and really easy, but it's something that we have to do. And compiled code has to do this. So this is one we have to know ahead of time when we AOT compile that this is actually pointing, that this is actually a compressed reference, not a full reference, and that we have to actually manipulate it before we can use it in its raw form. So it's really cheap and easy to do, but a more complicated example is what if the heap is somewhere between 4 and 32 gigabytes? Well, surprisingly, we can actually do compressed references there too. And the trick is that on a 64-bit platform, there's alignment requirements, right? So we have to basically start everything at a multiple of 8. The address always has to be a multiple of 8. And so that means that in the address, the least significant 3 bits are always going to be 0, which means, of course, if it's invariant, that's redundant information. We don't need that. So that kind of expands the ability of the largest amount of address space that we can reason about to 8 times what it was before. So that gives us actually a 32 gigabyte chunk of space that we can reference with just 32 unique bits. And so we just kind of take that out, the only part that matters, so to speak, and this is what gets stored in the heap, and then everything else we sort of just throw away. But again, there's a cost to this, not so much in performance at runtime, but in complexity. So when we compile, now we need to be aware that not only do we have to add some base address where the heap is located, but we also have to shift the address 3 binary digits to the left or right, depending on if we're compressing or uncompressing the reference. Interestingly enough, this shift is basically free because the CPUs we support allow for move instructions. There's a scaling factor that's built into the instruction. So we can go up to, we can multiply by up to 8 when we do these moves. And so there isn't actually a shift instruction that's added to the outputted code. It's all compact in the same move instruction. So we get this for free, but the AOT compiler has to be aware of it. It has to know to do this, and this is why we have to match our VM options. The other thing is garbage collection strategy. Now, garbage collection is a huge topic with a whole bunch of very complicated details, none of which we really have the time to cover. But just to give one example of why you need to be aware of what garbage collector is going to be used when you are compiling for it, whether it's JIT compilation or AOT compilation, is the necessity of write barriers. So write barriers are basically a way that we can use to avoid having to do mark for the entire heap. And when I say mark, I'm talking about mark as in mark and sweep. When we want to look at the heap and we want to identify which objects are live versus which ones are dead, obviously, for a very long time, we've used a technique called generational garbage collection based off of the generational hypothesis. And that's where we divide the heap into an area where it's young, and then there's old, and I'm deliberately simplifying this dramatically. Obviously, G1 looks nothing like this, and not even CMS or anything. There's scavenger spaces, and the real implementation is much more complicated. But in general, sometimes we have parts of the heap that we care about, that we want to collect, and very frequently. We have other parts of the heap that we don't necessarily want to have to collect or mark very frequently. And so we have some division, and we want to handle them differently. So if I come in and I'm trying to do some sort of concurrent collection, for example, and I'm, an execution or mutator thread comes in and creates a new object and then modifies some field of some other pre-existing object on the heap to point to this new object. Well, this is okay, and we don't really need to keep track of this, because if this is the young space or the new space or the nursery or whatever it is in the actual garbage collector we're using, we're going to find this when we mark this area. So this is actually, fine in and of itself. But what if we have something in the old space or whatever region that we don't want to have to mark? This is the part of the heap that we don't frequently go in and try and collect. Well, if the code modifies an address pointer or an OOP that's here in the non-collected, the region we're not going to collect next, we need to keep track of this somehow. We need to do bookkeeping. And so what we do is we have something called a card table. And a card table is basically the data structure that's used for our write barriers. So what is a write barrier? A write barrier is additional code that we emit when we JIT compile or that the interpreter executes that says that if you write to something on the heap, if you change an address anywhere on the heap, you want to mark a little bit in this card table somewhere to say, hey, there's a change here. So each little chunk of the card table is just basically like a map that corresponds to, as it happens to be, 512 bytes of the heap. And so if there's since each of these can be thought of as a flag, if that flag is set, that tells the garbage collector that, hey, there was a change, whatever chunk of the heap corresponds to this one flag, there was a change there and you should go look at that. So now, when we modify any object, any object field or pointer field in an object, we just mark that there. And then here in the not young, we mark that there too. And then when we do a GC, we can do the young collection like we always would and mark the entire thing. And then we can just check the individual pieces of the part that we're not collecting to see if there's any incoming pointers. And this is tremendously faster than having to mark the entire thing. So that's in a nutshell how we do generational collection, and it's also how we do concurrent collection. The card table, the write barriers and the card table are integral to both of those parts of the GC. And I think knowing that, now it's pretty easy to understand that when we AOT compile classes, the AOT compiler needs to know what garbage collection algorithm we're using, because it would need to know whether write barriers would be necessary or not. If you're using parallel GC, we actually don't need the write barriers necessarily. If it was not a generational collector, it's not. There's some cases where we need different types of write barrier. There's different data structures that the GC uses that do or do not need to be updated, and it all depends on the individual garbage collector that you're using. But the key takeaway is that we need to know what the garbage collector's expectations are when we compile. So anyway, we have these 4 different kind of scenarios or 4 different types of AOT compilation that we can end up with as a result. And each one corresponds to a set of choice of garbage collector and when compressed oops is enabled or not enabled. And there's actually a known library names that if we stick these libraries under the lib directory of our JDK directory, the JVM runtime will actually find these automatically and use them. But it's only for a small subset of modules that are actually part of the JDK proper itself right now. So if you want to use your own, if you want to AOT compile your own classes, the only option you have today is to pass the library file name on the command line. But if you are doing a chunk of the JDK itself, a module from within the JDK itself, and it's one of these 5 packages, or I'm sorry, one of these 5 modules, one of these 4 or Java base. If it's one of those 5, then you can just stick the resulting library in the libs directory and the JVM will pick it up automatically. So we're out of time, but just to wrap things up, so the value that is added by AOT compilation here is that it really gives you faster startup, you reach peak performance quicker, you have a smaller footprint if you have multiple smaller total footprint if you have multiple JVMs running the same code, and we can even run on platforms that would otherwise disallow JIT. The risks here, the caveats, are that it's experimental, it's not documented, it only runs on Linux, AMD 64 today, and custom class loaders and invoke dynamic or ND are not supported. And of course, your mileage may vary. So there's other AOT sessions. This one was the introduction one. This one was just how to use it, whether the information you would need to consider whether you might want to use it or not to make that decision. And hopefully you'll walk out of here with feeling that you've learned that. But if you want a more in-depth talk, I'll look under the hood. These guys are doing a talk from that they also delivered at the JVM Language Summit, and this was excellent at the Language Summit. You can actually catch it on YouTube if you are unable to see it live today. But if you can fit it into your schedule, I strongly suggest going and seeing them live tomorrow. And then also there's another session I don't really know the details about, but someone is doing a kind of more, I guess, fundamental talk about some of the principles involved with static versus AOT compilation. So it should be an interesting talk. So thank you very much for your time. I very much appreciate. Oh, sorry. Oh, it's your talk. Okay. Well. Yeah. So I'm sure it's going to be a great talk. All right. Thank you very much for your time.